Hi, this is Mrs. Cribb, and we're going to go over a complex thermodynamic problem. I'm going to start off with ice, and we're going to start at this point right here. And that's where we're going to have ice at negative 10 degrees Celsius, and we're going to have 7.5 grams of this ice. We're going to heat the ice up. We're going to melt it. So then we're heating up to this spot, and then we'll melt it to get to the other side, to here. And then we'll heat up the liquid water to get it to be hot water. And then we're going to turn our hot water into gas. And then we're going to heat up our water all the way to this point right here. So we're going to go from 7.5 grams of ice to 7.5 grams of steam at 120 degrees Celsius. Okay? All right, so this is going to require several steps. And we're going to start off with calculating each amount of heat. Now notice we're adding heat. So this first area right here, and this first part is Q1. In Q1, all we're doing is heating up the ice from a negative 10 to 0 degrees Celsius. So this is called the slopes. When they're like this, these slope lines represent the areas where you have sensible heat, the heat that you can feel. And when you have sensible heat, the formulas you use for sensible heat lines are Q equals mc delta T. The M stands for mass, the C is the specific heat, and the T, the delta T, is the change in the temperature. All right, now the flat parts are the parts that I call the lazy areas, right here and right here. Those are the latent heat areas, latent, lazy heat. And in latent heat areas, both of these guys, you're undergoing a phase change. You're not adding any more temperature change. You're adding more heat, but you're not increasing the temperature. And you'll notice right here, for this first section, the heat of fusion, the latent heat is where you use the heat of fusion, the delta H of fusion. You'll notice the temperature is 0 degrees here when we have 0 degrees of solid water or ice, all the way over to here. We still have 0 degrees 0 degrees water now. The temperature did not change. Then we have that sensible heat. We can see the temperature changing. We can sense it. We can put a thermometer in it and see that it changes until we get up to the top where we have right here 100 degrees of water. This is still water, but then the water turns into steam or vaporizes, and we're going to use the delta H of vaporization on this latent heat area until it turns to 100 degree steam. Again, the temperature did not change. In the latent heat, the temperature does not change. Once it's all the way changed over to steam, then we heat the steam back up again, and so we have another sensible heat area right here. All right, and the sensible heat areas, we always use Q equals mc delta T. So let's start off with actually Q1, which is this area here where we have ice. Okay, this is all ice, and all it's doing is heating up. So for that first area, all sensible heat areas, with Q is going to equal mc delta T. Right, M stands for the mass. So that's the 7.5 grams. So in that case, just write that down. M is equal to the mass. I know before little m was the molality, but here it's the mass, and we're going to have to keep that straight. 7.5 grams. C is the specific heat. And we have to look that up, specific, on a chart. And so I have a chart we can look at. We pull that up. Here it is. Specific heat of water, 4.18 grams, 4.18 joules per gram degree Celsius. So the unit's not on this one, right? So I probably should take care of that. All right, so the specific heat for water is 4.18 joules per gram degrees Celsius. All right, so now I'm going to write that in here. 4.18 joules per gram degrees Celsius. And then we're going to multiply it by the change in the temperature, delta T. Now, delta T, remember that delta T is always the final temperature minus the initial temperature, no matter where. So we have to compare the temperatures here. So for the ice section, the final temperature, when it starts off actually here and it ends up here. So for that first section, the final temperature is 0. So 0 minus a negative 10. Okay? And so 0 minus negative 10, just do that, and that becomes a positive 10 degrees Celsius. So the temperature went up by 10 degrees. If it had gone down, it would be a negative value. But it went up by 10 degrees. So now we're going to pull up our calculator and do the math. There it is. Scoot it over so we can see it. Okay. All right, 7.5 times 4.18 times 10. 313.5. 313.5. So I'm going to write that down. 313.5. 313.5. Now, what is the unit? Well, notice right here the grams cancel with other grams. And also notice the degrees Celsius cancels with other degrees Celsius. So the only unit that wasn't canceled out is joules. Now, what about our sig figs? Now we are going to worry about sig figs. The only thing really measured here, there's two things measured really, the 10 degrees Celsius and the grams. And I'm going to go ahead and just add a decimal to our degrees so that we can have at least a 2 sig fig answer. So this is 2 sig figs. So I'm going to change this to 2 sig figs. That would be 310 joules. Now what does that mean? It took 310 joules for it to go from a negative 10 to 0 degrees. A negative 10 to 0 degrees, it took I had to add in 310 joules of heat. All right, now we need to calculate Q2. And Q2 is the heat from this area. And here we have a liquid. I'm going to draw it like this, a liquid. And it starts off as a ice, and we turn it into the liquid over here. By the time it gets on this side of it, it's a liquid. Over here, it's still a solid. So it's just working its way from a solid 0 degrees ice to cold 0 degrees liquid. So let's calculate Q2. Q2. Now, Q2 is in the latent heat of fusion area. So we have to use this formula. The moles times the delta H of fusion, the heat of fusion. Now, I don't have the moles of water, so I do need to change it over to moles. So 7.5 grams of ice or water and 1 mole of water. And so I need the molar mass. So I need to calculate the molar mass. So I'm going to do that right down here so I can put it in that spot. H2O. So 2 H's, 1 oxygen. Notice this, H is, there's 1.01 grams per mole. Multiply 2 times 1.01 and add 16, we get 18.02 grams per mole. All right, that's what I'm going to use here, 18.02. Now I'm going to calculate how many moles I have. Let me turn my calculator back on and scoot it over so we can see the work. We have 7.5 divided by 18.02, and that gives me 0.416, and there's 2 sig figs, so 0.42 moles is my answer down here. So 0.42 moles. Okay, that's what I can use in this formula. 0.42 moles of water. And now I need the delta H of fusion, which is a value you get from a chart. So we're going to go look at the chart one more time. And let's see. I don't have the delta H of fusion on this chart. I guess I need to go get that real quick. Okay, I went and got the values. There it is. Ta-da! Okay, the molar heat of fusion, which is changing it from a solid to a liquid, is 6.01 right here. 6.01 kilojoules per mole. So that's what we're going to need to use. 6.01 kilojoules per mole. So let's write that in. Where did my pen go? 6.01 kilojoules per mole. Now I want you to notice again, moles in the numerator, moles in the denominator cancel. So now we're going to calculate what Q2 would be. All right, I'll pull up my calculator. Scoot it over so we can see. Turn it on. All right, 0.42 times 6.01 equals a 2.5242. Now there's two sig figs, so we're going to do 2.5. Let's write that down. 2.5. And notice it's kilojoules. So this is that's Q2. So now we need to calculate Q3. And Q3 is this area right here. See, right now what we've done, we've gone from here to here, we've added that much heat, and now we've added more heat to get it to this section, and now we have to add even more heat to turn it from 0 degrees liquid to 100 degrees liquid. And since this is in the sensible area, again we use Q equals MC delta T. So every time you're in a sensible area, right here, and even over here, we're going to use Q equals MC delta T. So we're going to calculate Q3. MC delta T. All right, mass is still the same, 7.5 grams. The C is the same, 4.18 joules per gram degree Celsius. And the temperature change is different now. So it's temperature change is T final times T initial. T final times T initial. All right, the final temperature in Q3 is right there. There's the final temperature. The initial temperature in Q3 is right there. So the final temperature is 100 and the initial temperature is 0. There they are. So it's 100 minus 0 degrees Celsius. So that's just 100 degrees Celsius. So again, we got some cancellation to do. Degrees Celsius cancel, grams cancel, and we'll be able to have joules. So let's pull up our calculator and calculate this section. All right, 7.5 times 4.18 times 100, 3135, and it's two sig figs, so 3100. 3100 is my answer. 3100 joules. All right, that gets us all the way to this point. Now we're going to keep going. We got Q4. I'm going to scroll up a little bit. So Q4 is now back into a latent area. See? Latent lazy heat area. Where it is. So we're going to need the delta H of vaporization. Since it's similar as the Q2, it's still going to be moles times, but this time instead of the heat of fusion, it's the heat of vaporization. The moles we already calculated. The moles was 0.42 moles. And I'm going to go look up the vaporization number on the chart. And this time it should be there. All right, water. Aha. Now there's the vaporization number, 40.7 kilojoules per mole. There it is, 40.7 kilojoules per mole. So let's go back and put that in, 40.7 kilojoules per mole. 40.7 kilojoules per mole. And now I just need to calculate that part out. Pull up my calculator. Scoot it over again so we can see. Turn it on. All right, 0.42 times 40.7. And this time I get 17. Again, two significant figures, 17. So, two significant figures, 17 kilojoules. So this is Q4. Here's Q3. Here's Q2. Whoops, 2.5. And Q1. All right, we have, that gives me to this part right here, because this was Q4 we calculated. Now we have one more little section, this little section here. So what have we done? Now we added the heat necessary right here, this amount, much more heat to go from the 100-degree liquid to the 100-degree gas. And now it's a gas, and we're going to add just a little bit more heat to go from 100-degree gas to 120-degree gas. Now that's again a sensible heat area. So we have one more Q to calculate, Q5 this time. And since it's sensible heat, it's MC delta T. The mass is 7.5 grams. The C is 4.18 joules per gram degree Celsius. And the delta T this time, what's the delta T? Let's look at it. T final is right there. And that is 120 degrees. T initial is right here, and that's 100 degrees. So the final minus the initial is going to be my delta T. Final minus initial, 120 minus 100. So it's 20 degrees Celsius. It's positive again because each time the temperature is getting hotter. On all the sensible areas, the temperature got hotter. But on the latent lazy areas, the temperature did not change. So we're going to multiply it out and find out what Q5 is. Okay. We have 7.5 times 4.18 times 20. 627. Now again, I'm going to make it 2 decimal places, so that 2 sig figs. So 627 would be 630. We're going to write 630. $630 joules. Okay, and that one, I should circle it with the blue. That is my Q5. All right, so that's all the pieces of heat. This right here is the Q5 area. And now to find out the total amount of heat it took to go from the very beginning over here all the way up to the very end over here. We just have to add up all pieces, all the heat. We have to add all Q's together. So the total amount of energy is going to equal to all the Q's added together. Q1 plus Q2 plus Q3 plus Q4 plus Q5. So that's going to equal 310 joules right here, plus Q2 is 2.5 kilojoules right here. Q3 3,100 joules. Q4 17 kilojoules. And Q5 630 joules. All right, now the only problem with this is that they're not all the same unit, so we do need to do a little bit of conversion. I'm going to convert all the kilojoules to joules, and you do that by just multiplying by 1,000. So this becomes 2,500 joules. This becomes 17,000 joules. So to change kilojoules to joules, you just multiply by 1,000. Okay, now just add it all together, and that will give me my final answer for this question. All right, so here we go. It is 310 plus 2,500 plus 3,100 plus 17,000 plus 630. I got 23,540. 23,540. 23,540. Now, joules. Now we got to figure out what the sig figs. When you're adding, you look at decimal places. Unfortunately, the one that's the least precise is this one. It only goes to the thousands place. So technically, I should end right there, and my number would be 24,000 joules of energy right here. 24,000 joules of energy to heat up 7.5 grams of ice to make it 7.5 grams of steam at 120 degrees. And the ice started out at negative 10 degrees. All right, if you have trouble with this, just review it and think about it again, and hopefully this will help.